Question 2. Around the bend. A rider rides around a circular bend of radius 7 meters at a constant speed of 10 meters per second. So I think, yeah, here's a diagram down here. So radius of 7 meters. Let's draw in our beautiful circle. Radius 7.0 meters. And the cyclist, I'll just use a dot, is traveling at a speed of 10 meters per second. 10 meters per second. There we go. So if the combined mass of the rider and the bike is 90 kgs, that's our mass, calculate the centripetal force. Centripetal force required, denoted by F subscript C. Cool. So the centripetal force is a net force. That means it's not a force itself. So in this case, the rider, as they go around a corner, their tires making contact with the ground result in friction, and that friction is pushing them in to this circular path. Right? So the net force is always acting inwards. That's actually what centripetal means. Inwards, or like towards the center. So as they go around the circular path, the ground pushing against their tires, right, that friction keeps them in that path, right, by changing their velocity, right, the direction of their velocity each time. So in this picture I drew it 10 meters per second down, but in a second or two it'll be at a slight angle, and it keeps changing the velocity, right, the direction. In this case we're assuming the magnitude stays at 10 meters per second. Great, so as you can see I've just drawn a sun here. That's how that ended up. Anyway, I hope you get the idea. So centripetal force is not a force, but it is a net force. In this problem, it's caused by the friction. And we can, just like with Newton's second law, if you remember, F net equals mass times acceleration. So that was like the net force on a block, for example. We can calculate the net force using the mass, but instead of linear acceleration, right, straight line acceleration, we use circular acceleration. So let's have a look at our formula book. So on the third line we see AC, A subscript C, equals V squared divided by R. So that's centripetal acceleration. And then below that, Newton's second law. And you'll see, if instead of using A, we use AC, we actually get the equation below. Centripetal force equals mv squared divided by r. So centripetal force, Fc, equals the mass times the tangential velocity, right? In other words, this constant speed squared, divided by the radius of the circular path. And that's all we need. So we can substitute in the known values. Mass of 90, velocity, or in this case, this constant speed of 10 meters per second, squared, divided by the radius, 7.0 meters. Alright, all of those are SI units, so we can just compute that directly. 90 times 10 squared, all divided by 7.0, to give 1,286. And the units for centripetal force, it's a force, or rather a net force, so it'll be newtons. Now that is correct. However, to be more correct, we would in this case use, I guess, two significant figures, right? Just as all the other values have that. So just round it up to 1,300 newtons. And that is an achieved question. Question B. So when the rider is in the position below, they bike across a very, emphasis on very, slippery part of the track. Use physics principles to explain the path the rider takes when they bike across the very slippery part of the track. Show this path on the diagram with an arrow. Awesome. So just a reminder, back up to this beautiful diagram. Oh, I just deleted it. Take two. So we had our circular path, and at a given point, their tangential velocity is 10 meters per second, let's say. The thing that causes them to stay in that path is the friction, which then changes the direction of their velocity. Right, and this happens not in distances like this, but constantly, right? That keeps them in that circular path. So if they cross a very slippery patch, there is no friction, which means there's no net force causing them to stay in that circular path. So they'll essentially slip out and then just travel in a straight line. So let's try put that into a few bullet points. So firstly, on the diagram, right, assuming they're pedaling forwards, I guess, their velocity, their tangential velocity would be like that, and it would stay like that as there's no friction on that patch. Cool. So some bullet points. On slippery patch, there is no friction, or at least very little, right? Okay, so we don't have friction. What does it mean if there is no friction? Well, no friction results in no centripetal force, What does that mean? So remember, a centripetal force is a net force, so this is another way of saying there is no net force. I'll just put in brackets. This is kind of repeating myself, but it'll help us with the next point. So no net force. Or alternatively, you could say forces are balanced. And from Newton's laws, if the forces are balanced, we know it cannot be accelerating, which must mean it continues in a straight line at a constant speed. So bike continues in a straight line at a constant speed. Right? Unless acted upon by an external force such as friction. However, we've assumed there is no friction in that patch. Cool. So this is actually a merit question. If you have, sort of like 3 of the 5 points, so 1 point for the correct diagram, and then 2, 3, I guess 3.5, 4. So correct diagram, no friction, no centripetal force, and continues in a straight line would get you the full merit. And of course, after they slip out, right, and let's say they go onto grass, then there would be friction, so then an unbalanced force would cause them to slow down unless they keep pedaling. Alright, question C. Some trail bikes have a spring suspension system. The spring constant is 40,000 Newton meters, or newtons per meter, excuse me. A rider of mass 80 kgs sits on the bike, causing the spring to compress. Calculate how much energy is stored in the compressed spring. Right, it's just like anytime you sit in like an office chair, for example, with a gas spring system in it, it compresses a little bit, and when you get up, the chair bounces back, and that's the stored potential energy turning into kinetic energy, right, as it moves. Alright, calculate the energy stored in the compressed spring. We are given a mass. We are given a spring constant, so mk. We are looking for energy. So let's have a look at our formula book. So the second line from the bottom, E subscript P equals half kx. So that is the potential energy stored in a spring, equals half times the spring constant times the displacement squared. Do we know the displacement? We do not. Okay, so how can we work out the displacement? Let's have a look again. There's also Hooke's law. So the force applied on a spring is equal to the negative of the spring constant times the displacement. So we could use that to solve for x, and then use that x to solve for the stored potential energy. There is of course a way to combine it into one equation, but I'll split it up into two just so it's a bit clearer. So finding displacement, or the spring displacement x, using Hooke's law. F equals negative kx. Right, so I'm just describing the step before I do it. You could jump straight into doing the step. So F equals negative kx. So what is the force acting on the spring? Well, that force would be the rider's mass resulting in a weight force. Right, so force would actually be mass times gravity, where mass is 80, gravity is 9.81 or 9.8, equals negative k. Oh wait, we do know what that is, don't we? The spring constant, 40,000. X is what we're looking for. Cool. Alright, so let's solve for x. So on the left hand side, 80 times 9.81, 784.8, equals minus 40,000 x. Now I'll divide both sides by 40,000 to get x by itself, or I guess negative 40,000. We'll talk about that negative in a second. Divides by negative 40, 1, 2, 3, gives negative 0.0196. 6 meters, because everything else was in SI units. Great, okay, so what does this mean, negative displacement? So the negative in Hooke's law just tells us that if we compress the spring down, the force opposing it would be up, right? They are in opposite directions. For calculating energy, we use half kx squared, half kx squared, and notice the displacement x is squared, so it doesn't matter if it's a negative displacement, because that'll end up being positive. So let's just substitute in what we have. Half k and again this negative, wait, excuse me, no negative here. K is just 40,000. Let's double check, yeah, 40,000. So half times the spring constant times the displacement. At this stage, if you just drop the negative, it's totally fine. Yeah, because they do mean the same thing in this context. Squared. Can punch it in on our calculator. 0.5 times 40,000 times bracket 0.0196 bracket squared to give 7.68. And our units for energy would be joules, right? Because everything was in SI units. So if we worked out displacement correctly, that would be achieved, and then working out the energy from that would be merit. Cool. So just to summarize that one, to find the energy stored in the spring, we had to work out its displacement using Hooke's law. And we solved for x, right, the displacement, and then we found potential energy using EP equals half kx squared. Right, so that's the potential energy stored in a spring. Right, if the spring constant went up, the potential energy would go up as well for the same displacement. Similarly, if the displacement went up by a little bit, the potential energy would go up by a lot because it's squared for displacement. Alright, and the last question for this entire question, part D. When a rider lands after a jump, they essentially have a collision with the ground. Hopefully it's their bike and the springs and not their face. Use physics principles to explain fully how a suspension system makes a bike safer for landing, right? Rather than not having a suspension. Alrighty. There's two decent ways of explaining this one. Let's go with the, I guess, common sense method, and then we'll use some level 2 physics equations to back that up. So first method, we just looked at in question C how when you compress the suspension system, it gets stored energy. So where does that energy come from? So in a collision, or rather a collision with the ground, as the springs compress, they will take some of that energy and store it as potential energy, which means less energy is transmitted directly to the rider over a longer time period to then reduce injury. So putting that in words, so this is, I guess, option 1. Spring absorbs energy when landing, right, and it's stored as potential energy. So of course the spring will bounce back, but not immediately. So it'll spread out that energy. So the spring absorbs energy when landing, less transmitted to the rider. Over a longer time period, so it spreads it out. Over a longer time period, which then results in less injury, or a lower chance of injury. Cool. So those 3 points would actually get you an excellence. Now the second way of explaining it is to consider change in momentum. So for a spring, or with or without a spring, the change in momentum would be the same, right? You're going from a velocity of, let's say, 10 meters per second down immediately to a velocity of 0 meters per second, and your mass stays the same. So change in momentum with or without spring is the same. However, what the spring will do is, instead of the impact being smack done, I was just imagining, anyway, let's not go there. It increases the time of the impact, right? It cushions it. So however the spring increases time of impact or collision, awesome. And now in level 2 physics, let's have a look at our formula sheet. Where is it? Oh yeah, delta P equals F delta T, so the change in momentum equation. If we rearrange that for force, so force equals change in momentum over time. So if time increases for a constant change in momentum, force would decrease. So smaller force as longer time, with same change in momentum, therefore safer. So just to recap that last one, with or without a spring, the change in momentum will be approximately the same, right? As you're falling, and when you hit the ground, your velocity becomes 0. However, with a spring, that collision will last maybe a second longer, which means the force acting on the rider is spread out over time, so it's not all in one go, and that smaller force is just safer, right? Reduces the risk of injury. And that argument would also get you an excellence. Awesome. Well, that's it for this question. Hope you have a wonderful day. See ya.